Okay, hi everyone, I'm Ali, and I'm going to talk about sequential nature of recommender systems and why it matters in the evaluation process. So let me say that datasets we have are frequently generated sequentially. And what does it mean? Let's focus on human-AR interaction. What we expect is that we might have a user side, a user at time M, and the AI side, which might be a supervised learning algorithm, let's say a predictor. And the predictor observes some features from the user and makes a prediction and observes the feedback. And for example, in the context of medical treatment, it might be that an AI assistant physician observes some symptoms, gives a treatment, or in the context of recommendation or recommender system, or what I call RS from now on, observes a context or previous ratings, recommends an item, and observes rating either implicitly or explicitly. So if this was the case, we could see that there's a system here, and the input is just a user drawn from a fixed distribution maybe, and the output is the feedback. So probably our data, which is a set of tuples like that, should be IID. But is this the case? I don't think so. So what's the problem? I mean, the point is that we always are collecting some history of the interactions and give them to an algorithm to update or classifier or register or let's say or recommender system. So that's what I call sequential nature of recommender systems. And I want to make a clear contrast here about recommender system sequential decision making versus human sequential decision making, which I think is helpful. Consider I have flight recommender systems that recommend some flights, something like that. And again, you can see that there is such a loop here that I call Rex's sequential decision making. My recommender system observes more and more user, makes better and better model. But on the other hand, we know that this person here might have some complementary preference. So we know this user probably after purchasing a flight will go and ask from another recommender system or in another task from the same recommender system about a hotel. So I call this human sequential decision making. And my talk is not about this part. I just will focus on a single task where my recommender system is just interacting with more and more people and just updates its model. Okay, now that it's clear what is sequential decision making and in the context of recommender systems, let me formally state the model. I assume that users and items can be represented with some vectors to be named U and I, and the feedback is Y, and the history I have is just UI, Y for times before M, if I'm in the time M. And okay, now that we know recommender systems are sequential decision makers, why it is important actually. So data we have, and we want to train our new recommender system or evaluate a new recommender system is actually collected by another recommender system, which I call the logging recommender system. And this logging recommender system is certainly a sequential decision maker, which try to maximize user engagement. So that is why we call data is collected sequentially. And why is this problematic or important? Because samples are no longer IID. It is important in both the training process and evaluation process, but I'm going to focus on the evaluation process. And the first conjecture is maybe these samples to be non-independent leads to overestimating generalization. But what does generalization mean here? Maybe I have to open a parenthesis here and define it. To define generalization, I have to define what is risk of a classifier, or here in the context of recommender system, risk of this F hat is the expected of loss of the predictions actually, given my user items and responses are drawn from a fixed distribution. We usually don't have access to that distribution. That's why we use empirical risk. Specifically, we set aside a part of the data and call it test data or whole lot data. And we know if My samples are IID with high probability. My risk is bounded with this empirical risk calculated on the test data. But if my data is generated sequentially, I would have a weaker bound here. So probably I'm just overestimating the performance of my classifier or my recommender system. That's the first problem and first conjecture. The second problem might be that the evaluation process might be prone to adaptation. And what is adaptation? I open another parenthesis here. So what is adaptive? What is an adaptive algorithm here? Let's say you want to train a series of classifiers or just a series of recommender systems. What do is that we have this f at time t given features of the test set. We make some predictions. This is the vector of predictions. And we query an evaluator. Evaluator holds the confidential test data. And we observe some feedback from the evaluator. Often this is actually the empirical test, the empirical error on the test data, but this does not end here, actually. That's why we call it adaptation. Adaptive algorithms try to just tailor their predictions towards the test data, and this is harmful, actually. This process actually naturally happens when we have a leaderboard and we try to make, and we actually submit our predictions and receive feedback, for example, from Kaggle. That's why we have different evaluation mechanisms. For example, the mechanism that Kaggle uses is just returning this empirical risk on the test data with some precision, for example, 5 decision point, I think. Recently, we have seen this ladder mechanism, which only returns the empirical risk on the test data if you have had a significant improvement. I'm not going to talk about this mechanism. It's just so much detail. But the conjecture here is that maybe if our data is generated in a non-IID scenario, we are more prone to adaptation. And how can we evaluate these questions? Our proposal here is to just maybe we can measure the robustness of our methods to adversarial attack. And this adversarial attack is different from what you might have in your mind. So I'm going to define what is adversarial attack. Adversarial attack is basically this adaptive algorithm I just explained. The adversarial attacker just queries the evaluator with many queries VT and observes the feedback and tries to reveal this Y test. But the difference of the adversarial attack to the adaptive algorithm I just explained is that adversarial attacker does not try to learn anything. It just has access to the features of the test data. So the aim is only revealing test part of the data without learning anything. And the robustness to adversarial attack is a good sign, actually, a good measure. The most well-known adversarial attack is this boosting attack. It's very simple. Don't look at the name. At each time step t, it queries the system with a random vector, with a completely random vector. Let's say we have a binary classification. It generates a random vector, observes the return risk. If the return risk is better than the chance level, it keeps and labels this vector here as informative vector. And finally, the prediction will be the majority of all informative queries. But as you might have seen here, this boosting attack and these queries, which are completely random, are sequence blind. So what we did was to design and tested actually 2 sequence-aware adversarial attack. And we did it in 2 different ways. The first one is in a model-free way, where we designed a random window boosting attack, or in short, WBoost, which tries to learn distribution over the sequence. If we have any distribution shift because we have cold start or other problems when we go over the time, this kind of attacker tries to learn that. And the other attacker, which is kind of optimum attacker, is named model-based. If we know what was the model of our logging recommender system, we could, given we have observed the order of the data, we could find the posterior distribution over the labels of the test data. And here we assume in the model-based, it's a simple model, it's a huge assumption actually, but it works. We assume that we approximate the logging recommender system with a k-nearest neighbor recommender system and find the posterior probability over y-test. And then rather than drawing these queries during attacking from a uniform distribution, we draw them from this posterior distribution. I'm not gonna talk about technical details here, so I would skip all these technical details. I just put them here if someone asks me what are these attackers. I'm gonna briefly talk about experiments. First of all, let's talk about the synthetic data. And what we did was to just simulate some data, and we assumed the logging recommender system is itself a k-nearest neighbor recommender system. And let's see what should we expect here on synthetic data, then we can see how significant are results on the real data. I'm gonna present a few figures like this, so let me explain them. On the x-axis, we have number of queries sent to the evaluation system, and on the y-axis, we have the average loss. So the lower is the loss, the more successful was the attacker. And we always compare an attacker with the boosting attack. And we know the boosting attack is sequence aware. So any improvement over the boosting attacks shows the importance of sequential information. Here we can see also, we always have two panels. The left one use Kaggle evaluation and the right hand use ladder evaluation. And here we see, for example, that this W boost gradually is learning the distribution shift, but it's kind of unsuccessful when the mechanism is ladder. And what about post boost? Post boost is kind of optimal mechanism if it has the accurate model. What we see here is that post boost is almost always about 3 to 5% better than the boosting attack, which shows the importance of the sequential information. And most importantly is here, when the number of queries is 0, what does it mean? It means that I have never queried my evaluation system. My post-boost attacker just looked into the order of the data and could predict the labels just based on the order they have appeared. That's because my logging recommender system was rational. I know my logging recommender system tried to maximize user engagement. So I observed this order of data and I can calculate the posterior distribution. And I see the chance level is not, although the data was balanced, the chance level is not 50%. And then we extended it to this famous movie lens 100K. I just simplified the problem to be a binary classification problem, downsample data to be balanced. And I obtained user and item representation from the context. And we somehow observe similar patterns here. Still, this W boost is able to learn the distribution shift over the time. And again, post boost is able to reveal some information about the data. Most interestingly, maybe, is that although data were sampled to be balanced, the chance level still is not 50%. Just before looking into the data, or post-boost attacker could reveal just 1% of the labels. So this is interesting, I think. So my takeaways are, the sequential information consistently makes the evaluation problem more prone to adaptation, maybe more than 1%. And they reveal 1% of the test data. We can say they disrupt the evaluation process for 1%. And is it actually important? 1% is significant or no? I don't know, but if you look into the leaderboard of this ML100K in the last 5 years, we have observed about 3% improvement. So maybe it is important, but actually maybe it is important. I mean, I never say that the ranking is gonna change. I said maybe the score we have obtained are just rounding to 1%, something like that. So just briefly about future works, I just used very simple model to model the logging recommender system. I use the KNN recommender system. People might use in future works more complicated ones and reveal more information about the Y test. I mean, the test data given the order of the observed data. But it needs a careful design and interpretation of the results. And finally, I only talked about the evaluation process, but sequential information also matters during the training time. We should make sure our algorithm is not learning that, because this is not something we want our algorithm to learn. I have to explain it later. But finally, we know that this missing not at random problem is very important in recommender systems. The distribution we obtain here might be helpful, for example, in inverse propensity scoring. And that's it. Sorry if it took longer than I expected. And feel free to reach out to me with this email.